Before we talk about muscles and get into all of that, I wanted to spend a few minutes talking about mass and weight and how gravity mediates the relationship between those, because it's not a super intuitive thing, and it is something that's very important for understanding how exercises work and where the difficulty of different motions of the human body comes from. This is all motivated from some of the stuff that we did last week with trying to adapt exercises for the International Space Station. This is part of the article analysis assignment that was due maybe a week or two ago. And I noticed some people had difficulty understanding which types of exercises would be more or would be less difficult in space when you don't have the action of gravity acting on mass. And I wanted to explain some of the finer points there, because it's not exactly intuitive. So just maybe a caveat here, a warning. Gravity is a really strange thing, and it took even the smartest people in the world many thousands of years to figure out how it is. So if this stuff seems counterintuitive, then don't worry. Nobody at all understood this until about 300 years ago. So if we're thinking about mass is really, it's just some amount of stuff. Like this kettlebell here might be 16 kilograms, which you could think about that as being some amount of, say, atoms. Right? Kettlebells are made of iron, so it's literally some, very large number, trillions upon trillions, but some large number of iron atoms that make up this kettlebell. And there's enough of them that we call that amount of mass 16 kilograms. And now the defining property of mass is that it resists the action of forces. So say your kettlebell is like sitting on the floor, maybe sitting on an ice skating rink, something with very low friction, and you kick it, you push it with some amount of force. If you know how much that force is, and you know how much the mass of the object is, we can predict how much it's going to start moving. Technically, we would say we could predict the acceleration. And the equation, if you've done physics, the equation that you're probably familiar with is this F equals ma. ma. So if you apply a force to some object with some amount of mass, it's going to start accelerating, meaning it's going to change its velocity or start moving, proportional to the mass. So the heavier the kettlebell, the harder it is to get it moving on the ground. Again, in this idealized situation of object sitting on frictionless floor and you're pushing on it laterally. So we haven't talked about gravity yet. So let's talk about how gravity acts on mass. Like I said earlier, gravity is a very strange thing. It's like this invisible force field that comes out of objects with mass, such as the Earth, and it pulls at a distance, almost like telekinesis. It pulls on objects that have mass, and it pulls on them exactly proportional to their mass. So gravity is like an invisible force field that's pulling the mass, the physical atoms in the kettlebell are getting pulled in this direction towards the Earth, which is a big, gigantic ball of mass below you. And that pulling is dictated by the mass of the Earth, and it just so happens that the math works out so that gravity will always pull on something, meaning it will create a force equal to 9.8, which maybe is a number you're familiar with, times the mass of the object. So when I teach K391 biomechanics, we talk quite a lot about calculating weight from mass and vice versa. The thing to know, though, is that what weight, don't need to know how to do the calculations. You do need to know that weight is a force that is created by gravity acting on mass. And that weight is proportional to the mass. Now, here on Earth, because imagine all of you have spent your whole life on Earth, we don't really perceive a difference between mass and weight. They're like the same thing because gravity is always the same. But that's not the case up in space, where you don't have gravity because you're on the International Space Station. So swinging a kettlebell around on the International Space Station is super easy. Now, it's not completely effortless, and the reason it's not completely effortless is because that mass gives the kettlebell some inertia, which means it resists being pushed around, just like our kettlebell sitting on an ice skating rink here. So it's not completely effortless to push a kettlebell on an ice skating rink around. And it would be more difficult to push around a bigger kettlebell, right? However, pushing a kettlebell on an ice skating rink is much easier than lifting a kettlebell vertically off the ground against gravity. So that should maybe convince you why any weight-based exercise on Earth, like kettlebells or barbell squats, are impractical to do in a situation where you don't have gravity without some modification. But even for machines that maybe don't immediately seem to be generating their resistance from gravity, like this lat pull-down machine here, if you follow the cable of the lat pull-down handle, you'll notice it goes up, it goes around a pulley, and then it's attached to this weight stack. And this weight stack has some mass, and that mass is pulled on by gravity down, of course, towards the center of the Earth. And that is where the resistance for this exercise comes from. So even an exercise like this needs to be modified if you're going to do it, say, on a space station where you don't have gravity. So the equipment that NASA actually uses on the International Space Station is this machine, which uses vacuum tubes. So there's a tube of empty of air. It's like a cylinder, and by pushing and pulling on that cylinder, it creates compressive resistance by virtue of the gases inside and outside. So this is something, just like pushing and pulling on a syringe maybe has some resistance, this is something that is not dependent on the action of gravity on mass to create resistance. So like I said, don't feel too bad if this is a little bit confusing, because it was confusing to everybody in the world until relatively recently. But this idea of mass resisting forces is something that we'll come back to later on in this unit, and indeed we'll actually even start developing an intuition about what it means for mass to resist not just linear forces like this, but rotational torque, so being spun around. But that's something that we'll talk about in a different video.